Welcome to part 2 of me trying to read Milne's prediction of the cosmic microwave background radiation. I'm Jonathan Doolin, and my claim here is that Milne actually predicted the cosmic microwave background radiation in 1935, though he is not given credit for it. This is Note 7 from the appendix of Milne's 1935 text, Relativity, Gravitation, and World Structure, available from archive.org. Note 7 is entitled The Apparent Brightness of a Receding Nebula, but he does not actually know the absolute brightness of the receding nebula. He only intends to figure out, given its absolute brightness, how you could come up with the apparent brightness of the receding nebula. And we've come to the middle of page 355, right after figure 20, where Milne says, for convenience, we consider first the case of any uniform relative motion of source and receiver, not necessarily one of pure recession. Now, I'm not entirely sure how convenient this is, but it is certainly more general. I can only presently describe my current impression of the meaning of things in this diagram, though as I go over it more, I expect I will become more confident. I will become closer to his intended meaning. I will come closer to his intended meaning, and I will become more confident that he means what I think he means. Let me follow the text then, line by line. It says, primed symbols refer to B's measures. So this, and this all refer to a measurement from B's perspective. And the non-primes, which include V. V is the only one in here that is non-primed. Of course, the M and the N and the P are all surrounded by brackets. But really, the only thing here in this diagram that refers to a shared perception is that velocity v. It says, let ds sub naught prime be a radiating surface centered at point B with its normal in the direction of a unit vector n sub naught prime. So that means, like, basically I am thinking we're sort of imagining a radiating surface whose parallel rays are basically coming out in that direction. Now, this n sub naught prime is going to be later compared to this I prime, so that when n sub naught and I prime are aligned, then 100% of that 100% of that intensity is going towards point A. But if n sub naught and I prime are not aligned, like if they were 90 degrees from each other, then really hardly any of this light would get to there. We'll see that a little bit later, where we frequently see this I prime dot n, or I prime dot n sub naught prime. I dot n, if those two things are unit vectors, would be the length of I times the length of n, which are both 1, times the cosine of the angle between. So if cosine of 90 degrees is 0, and cosine of 0 degrees would be 1, I am pretty sure this equation, this I prime dot n sub naught prime, would have a domain of angles theta equals negative 90 degrees to 90 degrees. Because if all of the radiating surface were aiming light away from that point, then there would essentially be 0 intensity arriving there. So we're going to consider this, we can basically consider this radiating surface to be more like a laser. Oops. More like a laser light that's sending out a light in a single direction, rather than thinking it, or just that small part of the surface that, of course, diagram is not drawn that particularly well here, but the implication is that that laser light is actually striking point A. Now, understand that I'm talking about a current impression here. I am not 100% confident that this is the way he was thinking of it. I'm also another way he may have been thinking of it is that the light was coming out from a sphere, like a spherical surface. But I don't think that that is a good representation. Well, I think that, well, maybe it is, because then you're going to have that per meter squared coming out of here, and then the steradians would be measured from, instead of being measured from inside the optical system, like this, if this was the pupil of the eye, if this, and this was the retina, or optical disc of the eye, so from the pupil to the optical disc, the pupil to the retina, and measuring the steradians there, you're actually measuring the steradians from here, in which case then we would not be constrained to a laser. We would think of each individual point producing light going out in all directions. And so the intensity of the light in the forward direction, the intensity of the light in the forward direction would be cosine of 0, and the intensity of the light in that direction would be cosine of 90, which would be 0. Cosine 0 equals 1. And so in essence, we'll have a watts per meter squared coming off of this thing, and you can measure exactly how much watts per meter squared that's producing. And then in a particular direction, we're going to have watts per meter squared per steradian, watts per meter squared is for this particular object. Watts per meter per steradian may be different over here than it is over here, and it'll be a different intensity through that region than it is through that region. You'll have a greater amount of intensity coming through this direction, which is proportional to cosine of 0 degrees, and you'll have a smaller amount of intensity coming in that direction, which is proportional to cosine of some angle theta. So it says let ds of naught be a radiating surface centered at the point B with its normal in the direction of the unit vector n sub naught prime, and let ds prime be a receiving surface whose center at the epoch t prime. I think I need to fix something here, because if this were t prime and this were t prime plus dt prime, then this could not be t prime and t prime plus dt prime. We need to have a different value of t prime here. So that's a factor that needs to be taken into account. Also, if we want to use notation that is consistent with his, I would need to actually label this x prime, t prime, because this is in the reference frame of the nebula, and we would want to say that that is domain theta prime equals negative 90 degrees to positive 90 degrees. So in my impression, this ds prime, he's drawn it here as an oval, and I've been thinking that oval was due to the idea that this cylinder was drawn obliquely. That for some reason we've set up this image so that it's pointing up, but it's facing us. Now that would not be a good way of doing it, because we want the observer to be facing directly at the source. There is a bit of maybe there's a bit of that, because if you have this object going upward in this picture, then the light that is traveling almost exactly parallel to that surface can actually be intercepted by the motion of the object upward. So that's part of it. But then there's another part of it, that this surface might be Lorentz contracted if the velocity is sufficient. But let's see if we can keep it simple without invoking all of that complexity. There's a single emission event here at location B at whatever time you decide it's sent. Maybe, okay, let's even say that it's emitted at t equals 0. We'll say, for sake of argument, and then that emission event arrives here, splits out, and gets spread over that area. And so all of those events may happen at different times in different positions, but that surface M is a locus of events where the event B, no, not event B, emission event at B at time t equals 0, t prime equals 0, is observed on the surface area of ds prime. So that locus of events might be spread out through space and time, because photons that reach the closer part of the surface since that thing is outrunning the light, parts of that event might arrive at that locus a little bit later than other parts. But there's two reasons that appears oval. One, because of aberration, you end up having to kind of tilt the area so that that surface is aimed square at that event. And the other reason is Lorentz contraction, which would make the length of the aperture be slightly contracted in the direction of the motion of the aperture. Okay, now watch this. Cool, huh? I can make the text go under so we can read more of it. Where were we? So ds prime is a receiving surface whose center at the epoch t prime in B's experience. So only its center. The center is at the epoch t prime in B's experience, i.e. at t prime by B's clock, is at the point A. So we will have an event A, comma, t prime is that event. Wish they would separate and have a variable and a constant. That would be nice. But because saying at one point this one is point B, comma 0. So this event is B, comma 0. This event where that light reaches the surface is A, comma t prime. And that's just the coordinates of the center. So it doesn't have all of those times and distances. Okay. Let n prime be a unit normal to ds prime. Okay, so v is right here. Whoops. Nope. V is the velocity, and n prime is a unit normal to the surface. Now, in this diagram, those appear parallel. They appear parallel, but does that mean to imply that they actually are parallel? Because we're going to have a surface that, well, I think basically, for the most part, unless it's a really ridiculously high velocity, n prime is going to be pointed somewhere between here and here. So it's not going to be parallel to the velocity, but it's also not quite going to be pointed straight at point B. It's going to be somewhere in between because of the aberration and Lorentz contraction of the surface. But this is the surface that, from the perspective of A, is pointed directly at event B. But it would take some additional work to figure out exactly what direction that n prime is pointed to be normal to ds prime. So then let v be its velocity. That's fairly simple and straightforward. Then let BA equals r prime. That's the distance from this event to this event. Just B minus A, basically. It's because we're considering that distance in the reference frame of the nebula. And let I prime be a unit vector in the direction of BA. That's this vector here. Then d omega prime, that is this solid angle. This d omega prime is equal to ds prime, that is this Lorentz contracted and aberrated surface, times I prime dot n prime. That is this direction, and n prime. N prime? Okay, yeah. Once you account for Lorentz contraction and aberration, if that surface actually ends up being a flat, completely zero. So if, after accounting for Lorentz contraction and aberration, n prime is perpendicular to I prime, or angle n prime comma I prime is greater than 90 degrees, actually, if they're not pointed towards each other, what would that mean? Well, it means basically if this beam if this beam is aimed completely away from this beam, if this telescope is pointed away from this nebula, then there won't be any light arriving from that event on that telescope surface. So if after accounting for Lorentz contraction and aberration n prime is perpendicular to I prime, then no light will reach the surface because the surface is not aimed at the nebula. I think it's kind of unfortunate that he drew the diagram with representing n prime and v being parallel, but what it should be is n prime is generally aimed towards b, but in the limit as that the telescope approaches the speed of light, it actually kind of needs to be aimed parallel, or it needs to be aimed closer and closer to velocity v to be aimed directly at the light from this event. It's kind of like if you're driving in falling snow, and your car is driving along. If you want to look at the origin of where that snowflake came from the point of view of that snowflake, actually you've got options in this case. You can be driving your car. These are horrible cars, I'm sorry, not a great artist, but you've got options in this case because you can control the speed of your car. Well, you could view the origin of that snowflake event from here, and it would appear to be the snowflake was coming along a straight line path to you, and which is the only option for light. You can't view while this guy sees those things coming down. He's never actually going to see any of those. If those were light rays, he wouldn't see any of those. But if he were driving really fast, then he could see that snowflake coming straight at him if he drove really fast, and all of these snowflakes would kind of look like they were falling straight at him if he picked up his speed. So in order for this guy to see all of the snowflakes kind of remaining in a single position but getting bigger, he would need to point his camera in that direction. But for this guy who wants to see this snowflake remain in roughly a stationary position, he needs to point his viewer in that direction. And if somebody going even faster would need to point their viewer almost in straight that way to see the snowflake stay in a constant position. Anyway, once again, this video has gotten a little bit long, so I'm going to cut it off here and proceed with another video in a little bit. Thanks for watching.